Intramolecular forces versus intermolecular forces. Intramolecular forces are pretty much the bonds between the elements. So if I take a look at H, O, and H, the intramolecular force is going to be that covalent bond between hydrogen and oxygen. An intermolecular force is the attraction between two water molecules, indicated here by this dashed line. So when I'm looking at the differences between these bonds, I'm really looking at strength. Intramolecular forces are stronger because they are sharing those electrons, while the H and the O in this case are not. They're basically going to be having some sort of electrostatic attraction or repulsion. Hence, water can also attach itself to another water molecule via these intermolecular forces. The first type of force is called an ion dipole. And an ion dipole is the charge between an ion and a polar molecule. So if I take a look at water as an example, water has a positive and negative charge, indicating that it could attract to something like a positive charge, like a sodium. And in this case, sodium has a positive charge, where it would attract itself to a negative charge in water. And that's the reason why sodium chloride dissolves in water, is because you have that attraction. Similarly, in water, you have chlorine ions. And again, there is going to be a situation where that negative charge attracts itself to the positive charge of the water molecule, in this case, the hydrogen. So ion dipole is basically when you have that dipole moment and you're attracting that to an ion. And again, classic example is sodium chloride. Sodium, as you can see from this diagram, has a positive charge, and as water is attracting to sodium, it's using a negative charge on the oxygen, thereby making that attraction and thereby dissolving salt. However, on chlorine side, everything gets flipped around, as indicated here by the partial positive and partial negative charge, as indicated in this picture. So they surround the sodium chloride ions, and hence sodium and chlorine are able to dissolve in solution. Now, moving along to the ion dipole and Coulomb's law. Generally, what we talk about is Coulomb's law in regards to the force of attraction. And we've already talked about Coulomb's law in the past, where Q is going to be considered the charge, and D is the distance between those charges multiplied by a K constant. So the general rule for this is that if the attraction increases if the radius of the ion decreases. So that kind of makes sense, right? If this D gets smaller, the force is going to get larger between that ion dipole. Similarly, if the Q value gets larger, you're also going to have an increased F. And the reason why is because that Q value is going to have a much larger numerator. And the magnitude of the dipole on the polar molecule also increases. And so when we're talking about this dipole effect, we're really talking about that polarity, that force of attraction between those based off the Q and the D. Here's another example of something where you have a dipole versus a dipole. And this classic example here is when you get two dipole molecules, one negative side attracts to the positive side. And again, we're taking a look at water as an example, where you have a negative charge on the oxygen and a positive charge on the hydrogen. So molecules with dipole moments experience Coulombic attractions when they're in close proximity to each other. And so again, the force of attraction will increase as the magnitude of the dipole increases. So again, the bigger these charges are going to be, the more likely you're going to get that dipole attraction. And so when you're talking about Coulomb's law, you're really talking about that idea of dipole to dipole interactions. Now, the way the dipoles orient themselves is they usually attract themselves by alternating the charges. And so what you're going to find is that the attractive forces are going to be very strong, while the repulsive forces are going to be very weak. So if I arrange the water molecules in such a way as putting a negative and a positive charge, negative and a positive, and I go ahead and create a little box around here, this would definitely minimize that repulsion, very similarly to kind of like a crystal lattice during ion forms. However, in this specific case, you're definitely going to get a lot more attraction the closer these are. So if you take a look at a water molecule and how it's arranged, how these dipoles are put in, you can kind of see that this orients itself in such a way that it allows you to be able to maximize that attraction. Now, when they don't align and they basically are moving around, that's where you're going to get attractive forces being weaker and the repulsive forces being stronger. So in this specific case, you can kind of see that if we shift the molecules around, the charges are not going to line up as nicely as they did in the previous picture. And because of that, these charges are going to have a lot more repulsive forces, and you're not going to get that cohesion that you normally would get when the charges are lined up. And this kind of brings us to a part of polarity and of solubility, and also of this idea of making this molecule stable. As this becomes to get a little bit more loose, it turns into something like water versus something like a sodium chloride crystal where you have these charges going around. And so since these are moving around, you get a little bit more of that repulsion, and that eventually creates other effects. A third type of bond is going to be hydrogen bond, type 1, which is a dipole-dipole. Hydrogen bonds occur between fluorine, oxygen, and nitrogen, and usually with nitrogen, with at least one lone pair. So if I give you a hydrogen and I put F, O, or N, and I have that, these are going to be much, much stronger than any of the dipoles that we've talked about. In fact, they're about 5 to 10 times stronger than a dipole-dipole attraction. So if I ask you to rank these in terms of dipoles, hydrogen bonds are going to be high up there, just because of the fact that you have that high electronegative element next to that hydrogen. So the question is, why are hydrogen bonds so strong? And basically the idea is that the F, the H, and the O and H and NH are very polar. Because they're very polar, they're going to pull on that hydrogen, creating a very strong bond between. These atoms are extremely small, so any partial differences are going to be super highly concentrated. So if you take a look at a size of a hydrogen and a fluorine, very, very small, even with an oxygen and even with a nitrogen. So not only are the bonds close to each other, but they're also going to have very highly electronegative concentrations. The lone pair on an F, O, or N also increases the partial negative charge by creating that attraction to that hydrogen. So that lone pair really does a lot of effects here. It kind of yanks on that hydrogen and creates that ability for hydrogen to really stick with that highly electronegative element. Here's a classic example of a hydrogen bond between a water molecule and another water molecule. As you can see here, oxygen has 2 lone pairs and hydrogen has this attraction. And because of that, what you're going to start seeing is that hydrogen bond is extremely strong. And that provides things like surface tension, it provides things like cohesion, adhesion, and water is definitely the universal solvent. And one of the reasons why is because of its very, very highly polar nature, but also more importantly is the fact that these electrons are creating really strong hydrogen bonds with that oxygen. Without that, the water molecule would be really unstable and probably would evaporate really quickly, or maybe even not be in many different forms. And that's what gives water a very special characteristic versus the others, because of that lone pair, of these lone pairs plus the highly electronegative element. Here's another example of water and methanol. So if I mix water and methanol, which is a type of alcohol, I get water and methanol is soluble in water. And the question is, why is it soluble? And the answer is quite simple. If you take a look at hydrogen with oxygen, you can kind of see that it forms those hydrogen bonds. Same thing with hydrogen here and here. So it surrounds the alcohol, and because alcohol has a OH group or a hydroxide group, the hydrogen is going to be able to form these temporary hydrogen bonds between ethanol and also with water. And so again, let's keep that in mind, that hydrogen bonds can exist between the H and the O and can produce and also can exist between the H and O here. So that really allows the alcohol to be soluble in water. Here's another example of hydrogen bonds in acetamide. And acetamide is another similar structure. It has a boiling point of about 221. And what happens here is that you actually create a very strong boiling point, 221 degrees Celsius, just because of these hydrogen bonds. And the reason why is because they actually have this carboxyl group, which is the O and the C. And when the H and the O attract itself, they form hydrogen bonds very, very strongly, and because of its general structure, the boiling point is going to be extremely high, and so this gives an extra added strength to acetamide. Now, ethanol does not form hydrogen bonds. And the reason why is because hydrogen bonds is bonded to a carbon right here. And the hydrogen needs to bond with an F and an O or an N. And so in this specific case, because of that hydrogen is already built in there, ethanol doesn't really have that ability to do like we had in niacinamide. Now you can still make a case here, but since the O is already kind of filled up, it already has those hydrogens in there. Alright, well we'll finish off right here, and hopefully you guys can watch part 2.